I want to talk about trig integrals, and you know some trig integrals, I'm sure, already. Well, let me write the differential form first. You know that d sine theta, or maybe I'll say d sine x, is, let's see, that's the derivative of sine x times dx, right? The derivative of sine x is cosine of x dx. And so if I integrate both sides here, the integral form of this is the integral of the cosine of x dx is the sine of x plus a constant. And the same way, d cosine of x is minus the sine of x dx, right? The derivative of the cosine is minus the sine. And when I integrate that, I find the integral of the sine of x dx is minus the cosine of x plus c. So that's our starting point. And the game today, for the first half of the lecture, is to use just those basic integration formulas together with clever use of trig identities in order to compute more complicated formulas involving trig functions. So the first topic is to think about integrals of the form sine to the nth power of x, cosine to the nth power of x dx, where here I have in mind m and n are non-negative integers. So let's try to integrate these. I'll show you some applications of these pretty soon. Looking down the road a little bit, integrals like this show up in Fourier series and many other subjects in mathematics. It turns out they're quite important to be able to do, so that's why we're doing them now. Well, so there are two cases to think about here when you're integrating things like this. There's the easy case, and let's do that one first. The easy case is when at least one exponent is odd. That's the easy case. So, for example, suppose that I wanted to integrate, well, let's take the case m equals 1. So I'm integrating sine to the nth power of x times the cosine of x dx. I'm taking, I could do that one. Let's see if that's what I want to take. Yeah. My confusion is that I meant to have this a different power. You were thinking that. So let's do this case when m is 1. So the integral I'm trying to do is any power of the sine times the cosine. Well, here's the trick. Use this formula up at the top there to see cosine of x dx as something that we already have on the blackboard. So the way to exploit that is to make a substitution. And the substitution is going to be u is the sine of x. And here's why. Then this integral that I'm trying to do is the integral of u to the n. That's already a simplification. And then there's that cosine of x times dx. When you make a substitution, you've got to go all the way and replace everything in the expression by things involving this new variable that I've introduced. So I'd better get rid of the cosine of x dx and rewrite it in terms of du, or in terms of u, and I can do that because du, according to that formula, is the cosine of x dx. Let me put a box around that. That's our substitution. When you make a substitution, you also want to compute the differential of the variable that you substitute in. So the cosine of x dx that appears here is just exactly du, and I've replaced this trig integral with something that doesn't involve trig functions at all. This is a lot easier. We can just plug into what we know here. This is u to the n plus 1 over n plus 1 plus a constant, and I've done the integral. But I'm not quite done with the problem yet, because to be nice to your reader and to yourself, you should go back at this point, probably go back and get rid of this new variable that you introduced. You're the one who introduced this variable u. Nobody except you really knows what it is, right? But the rest of the world knows what they asked for in the first place. That involved x. So I have to go back and get rid of this, and that's not hard to do in this case because u is the sine of x. And so I make this back substitution. And that's what you get. So there's the answer. Okay, so the game was I used this odd power of the cosine here, and I could see it appearing as the differential of the sine. So that's what made this substitution work. Let's do another example to see how that works out in a slightly different case.